Okay, let's get started. Before the class, let's check our schedule together, the remaining schedule together. So we are here today, right? 23rd of May. And then the class project is going to be due on June 7th. June 7th. Then I'm going to ask you to come up here and give a presentation on your project. That will take, I think, 3 classes because we have roughly 19 students. So each class, one class, I think 5 to 6 students can come up here and give presentation. So I need 3 days. That means from I think this Wednesday, the 8th of June. Okay, the first day and second day, the last day, your presentation, right? 8th, 13th, and 15th. And we have final exam on 20th. Because last week, right? 20th. So June 20th of June, final exam, right? The last week. And the problem is, so 8th, right? Then the problem is, 1st of June, that is election day, right? And 6th of June, Memorial Day, right? Holiday, 2 holidays. That means I have only 1, 2, 3 days to give lectures, including today, right? Only 3 days to give lectures, right? So today I'm going to finish up the interrupted discussion. Okay, one remaining lecture, interrupt. Then if you check out our schedule, we have a bunch of topics to talk, but we don't have enough time to talk everything. So probably we have to skip. So probably we have to skip this cache discussion and TLB discussion and Jogel too. So last thing we are going to talk is trust zone. That is very important for security, right? This course is industrial control system design with security, right? So security is very important aspect we have to talk in this class. So that will take, I think, at least two lectures, trust zone. So again, today we will finish up this interrupt discussion. Then we skip everything except this trust zone. Right? So any question about anything before class? Okay, let's get started. Okay, so I have one last lecture on interrupt. Okay, so we've been talking about interrupt for I think almost 3 weeks, right? And one remaining topic I want to discuss is this one: software generated interrupt. Okay, SGI. That is ARM's terminology. Right? Software generated interrupt, and that is used to generate IPI, interprocessor interrupt. That is very important. Right? That is why I want to talk about that. So let's go through this PowerPoint. I'm going to ask you to read PowerPoint, then let me explain. Okay, better. Guyun, can you please read? Okay, then so skip this then SGI. This one, Gino, can you please? Done. Okay. Then there is SGI. Then this one, Q1, can you please? Skip. The last one, Taejun. You're not Taejun. Wonjun. Okay. Okay, so let me explain what is SGI. So before that, I think you remember this slide. ARM is providing three kinds of interrupt. First one is SGI, software generated interrupt, and unique ID, right? For each interrupt, unique ID is assigned. For unique ID is assigned to each IO device. For SGI, so ID number 0 to 16, ID number 15 are assigned for SGI. Then the rest is assigned for IO devices. So IO interrupt, but that is from private IO, and that is an ID number 16 to ID number 31. So this is 16. 16 IDs are assigned to IO devices, but private IO. Private. What do you mean by private IO? Each CPU has its own IO devices. For example, private timer. It has its own private timer. So we have studied private timer. Right? So that is one example of private IO. And CPU number 1 that also has private timer. CPU number 7 has its own IO. There is IO interrupt and the private IO interrupt. The rest ID number 32 to ID number 1019 that is allocated for IO devices, but those IO devices are shared. So there may be there is SGI, is 16, private peripheral interrupt, private IO interrupt, private peripheral interrupt. Then shared private peripheral interrupt, shared IO interrupt, shared IO peripheral, private IO, shared IO, and SGI. So three kinds of interrupts are supported by GIC. So you can think of it as just IO interrupt. Right? Those interrupts are generated from IO devices, and this one is special. This one is generated by software. As the name implies, software generated interrupt. But do not be confused with. So I told you, right? Interrupt. There are two kinds of interrupt: hardware interrupt and software interrupt. Right? But this one is not software interrupt. Right? Software interrupt is supported as an instruction in ARM. We have SBC instruction in ARM. Right? Intel INT instruction. x86. RISC-V environment core instruction. Right? So software interrupt is provided as an instruction. And SGI, it should be classified as a hardware interrupt because it is delivered to CPU through that connection, IRQ, F5 connection. So again, IO interrupt is generated and that is delivered to CPU through that connection, that physical connection. That is hardware interrupt. Same thing goes to SGI. Right? SGI, it sounds like software generated interrupt. It sounds like software interrupt, but it is not. It is not software interrupt. It is hardware interrupt because that is delivered to CPU through that connection, that physical connection. Then the question is, how would you generate this software generated interrupt? Okay, again, hardware interrupt, it is typically coming from IO devices, and SGI is also belonging to this hardware interrupt. So how do you generate this SGI? Super simple. Okay. So this distributor is providing a register called software generated interrupt register. Okay. So you write this register, then distributor will generate the interrupt, and then forward that into CPU interface. The CPU interface, check the threshold, same mechanism, same protocol. You have private mask register where you set the threshold, priority threshold. So CPU interface got interrupt from distributor, then compare that against this threshold. If the priority is higher than threshold, that is delivered to the CPU. Super simple, right? So the thing is, using store instruction, STR, because it is memory mapped register. Right? So you are writing some data to SGIR register. Then distributor will generate interrupt and forward. So then the question is, okay, so before that, let's talk about this SGIR register. So here, you can specify interrupt ID. It's 4 bit. So yeah, I told you, right? ID number 0 to ID number 15, 15. So 16 IDs are assigned for SGI. So to generate SGI, simply write interrupt ID here, number. So you have 4 bit. 4 bit means you can specify 0 to 15. 1 of 16, right? You can specify interrupt ID. Then also you specify what? The green. 2 bit. 00 means, okay, so you need to look at this orange box to check out the target CPU. 00 means you need to check out this target CPU, meaning you can send this software generated interrupt to CPU 0, CPU 1, or CPU 7, or everyone, depending on the setting. Right? So green 0, 0. Then you have to look at this orange box. You say all 8 ones. That means you want to send that interrupt to everyone. Should it in target list indicate corresponding CPU interface. If you say 01, specify 01, then you want to send interrupt to everyone. To everyone, to 8 CPUs except user. Let's say that guy, CPU 0, wrote some value to there, okay, with 01. 01. Then CPU 0 want to send interrupt to everyone except itself. Okay. And 10. 10 means send interrupt to yourself. Send interrupt to yourself. The 1 is also. So in this sense, it is that simple. SGI generated by writing to SGI register, and that interrupt can be sent to anyone in the system. Okay. Then the question is, why do you want to do that? Why do you want to generate interrupt? Right? CPU 0. Okay, CPU 0 want to generate interrupt, writing to here, then distributor probably send the interrupt to CPU 1. So that is called IPI, inter-processor interrupt. That kind of interrupt is called IPI. So why do you want to send the IPI? This one. First one, the booting process, startup process. Right? Think about your smartphone. Your smartphone has 8 ARM CPUs. When you turn on your smartphone, only one CPU is alive. Only one CPU is alive, and that CPU is doing system initialization. After system initialization, 8 CPUs, right? One CPU is alive. That guy is doing all system initialization, and then wake up other CPUs, the other CPUs. How to wake up other CPUs? By sending IPI. Right in here, send interrupt to everyone. That is one application case. Second application case of IPI is task dispatch. Think about operating system. So you have a CPUs, and operating system want to execute some task. Right? In your computer system, your smartphone, you have many different tasks are running at the same time, right? Task 1, 2, task 10, I don't know. Right? So you want to assign this task 10 to CPU number 7. If operating system want to assign task 10 to task number 7, then how that can be done? By sending interrupt. By sending interrupt to CPU 7 is in the middle of executing something. You want to interrupt this task number 7, then assign it. Right? Assign some new task. So CPU 0 send the interrupt to CPU number 7, then operating system task scheduler is invoked. Task scheduler is invoked, then the scheduler is assigning the task to number 7. So that IPI can be used to dispatch some tasks to specific CPU. And third application case is a little bit complicated. Right? TLB shutdown. How many of you have heard about TLB shutdown? Don't know. What do you think? What is TLB shutdown? You took my architecture class, right? Did we talk about TLB? And what do you think? What do you think the TLB shutdown is? Anyone? Okay, so in multi-processor system, right, we have let's say CPU number 0 and CPU number 1. And CPU 0 is generating virtual address, and that is that address got translated to physical address by this special hardware called TLB as physical address, and main memory is accessed. Memory is accessed with physical address, not this virtual address. So in the middle, somewhere in the middle, you have cache. Cache here, or cache maybe here, depending on the architecture. So cache. In this case, cache is looked up with physical address. If you miss the cache, then you have to access main memory to load the specific memory block to the cache. So that is the logic. And what is a TLB? That's the question, right? TLB is a cache. Cache for what? TLB is caching what? Caching? Storing what? So why TLB? Why you need a TLB first? TLB is what? TLB is that special hardware is there to support virtual memory. Virtual memory. Right? So at each application, you run Hello World program, and that program is using the whole the virtual memory space, it's virtual address space. Then to access the code and data, your code and data, you should access main memory, right? But you don't know where your code and data is located. The operating system is doing that management, right? So your code and data probably split into many different places, not in contiguous. Let's say, let me draw main memory. So that is main memory. And your actual code and data, probably your code, your Hello World program, right? Your code is here, the first page number 0, and second page probably located somewhere, right? Not consecutive in your application. And your data, the data you want to process, probably located in physical page, physical page number 0, physical page number 10, 11, 12, physical page number 5. So your actual program is located, located in many different places. It is not in consecutive memory location. In Hello World program, that is a physical address. It's physical address. Using physical address, you access the page, and your application program is executed from clean virtual space. Nobody is using this virtual space but your application, right? So let's say it is 32-bit. Then location 02, the last location 4 gig minus 1. Right? So your application Hello World program is fully utilizing this virtual space, right? From location 02, the last one, consecutive memory location. And someone should tell you, okay, the first page, this virtual page is located here, your code, and second page is located probably here. The third page is located here. it's a mapping, virtual page to physical page. The thing is, your application program is executed on the screen. Nobody is using the screen space for you, for your application. So somebody, right? Again, somebody should provide this mapping, virtual page to physical page mapping, and that is this mapping information is stored in main memory in page table in main memory is doing. Page table contains the mapping information, virtual page to physical page. It has many different entities. The problem is this page table is to translate this virtual address to physical address. You have to check out first this mapping information for physical page table. Then for translation, you have to read this page table. So main memory access, which is very slow. And then after you get translation information, you access actual code or data. That is the second access, second memory access. So every time CPU executes LDR or STR or instruction fetch, you have to access main memory twice. Page table access first. Then after translation, actual code or data access. So that is taking too much time. So that is why CPU has this special component called TLB. TLB is caching what? Caching, storing frequently accessed page table entities. If it's 1 and 2, these three entries are accessed recently, and TLB contains 1, 2, and 3. What does that mean? Then for address translation, probably you don't have to go to the main memory. You don't have to check out this page table, right? Because TLB is providing physical address. If TLB hit happens. TLB hit means TLB contains translation information. So virtual address to physical translation is done by TLB. You don't have to access main memory. And based on that, based on physical address, you access cache or main memory. Okay, if you miss the cache, then main memory access. If you hit the cache, then instruction or data is provided from the cache. So again, TLB is a cache. Sorry, cache is what? Temporary storage. Cache, right? You are caching, right? Temporarily storing. Cache is what? Cache is storing code and data. Code and data inside the processor. And TLB is caching, storing what? Storing translation information. Translation from page table. So TLB is a cache for page table. And cache is cache for your code and data. So, and then with that said, TLB is folding 1 to 3, right? Assume that your application program is multi-threaded. You could generate 2 threads, right? And first thread is running on CPU number 0, and second thread number 1 is executing on thread number 1. And these 2 threads are collaborating each other to execute your application program. So parallel program. Then these 2 threads are referring to the same page table. And what if this thread number 0 update this page table? What if thread number 0 update? Okay, 1 is now no longer contains valid mapping. I changed that mapping to 1 dash. Thread number 0. Then thread number 1. There is no way for thread number 1 see that page table update. So it is still holding this the old stale, right? Stale or old translation information. Somehow you have to remove. You remove that. Right? This guy is one dash, and this one is one dash. Right? Somehow you have to remove that guy. So how do you remove that translation information from TLB? So Hardware is not providing. Hardware is not providing that coherence mechanism for TLB. Coherence is provided for cache only. Cache coherence. Right? That is provided by hardware. But TLB coherence should be maintained by software. Okay. So how do you remove this? By generating IPI that TLB shutdown. TLB shutdown means, okay, so you have to shut down this guy, kick out, remove, invalidate this translation information, shut down. Okay. So that means you have to inform CPU 0 should inform to CPU 1. CPU 0 should inform to CPU 1. Okay. Using IPI, then interrupt service routine supposed to invalidate that TLB entity. That is called a TLB shutdown. Okay. Again, the reason why IPI should be sent in this case is because TLB coherence is not maintained by hardware. Cache coherence is maintained by hardware. Right? So if you have taken parallel computer architecture class, right? CPU number 0, CPU number 1. Then you have cache, right? Simple, one level cache. Then you have main memory. So main memory is shared by these two processors, right? Then somehow you have to maintain the data coherence between these caches. Assuming that you are collaborating, thread number 0, thread number 1. Thread number 1 are collaborating each other to execute your program. Simple example is for loop, right? 0 to I 100. So you are adding, everything. Okay. Plus, right? You are adding, all the elements. Then the first half, right? Iteration I to 0 to 50. Okay, that is executed in CPU number 0. So it is generating partial sum. And CPU number 1 is generating a lateral half, right? 50 to 100, right? Iteration. So it is generating partial sum. Then you have to merge these two partial sums together, right? And then think about that. Partial sum. How do you? Partial sum is the global, sum. Global sum. You have to update this sum with this partial sum. Right? So read this guy, sum, then update, right? So CPU number 1 is doing the same thing. This global value of sum, not local value. So what if this guy is reading, right? Sum. So initially it is 0. So it is adding something. Let's say it is the output is what is the result? 0 to 49. Add all the numbers. And I know 50-50, right? That is 1 to 100. I don't know. Okay, 1000. Okay. That is partial sum. And partial sum is 2000. Okay. So you need to add these two, right? And the expected result is 3000. Okay. Because you need to add these two, right? Then how do you update this guy? So why am I talking about this? So what you have to do is, you have to read. Okay, you have to read. You read, right? LDR, then add, then store. LDR load is partial sum. Right? So R0, R0, R1, then R1. So reading from is the sum, okay? Update. Reading from Azure sum, then add 1000. Okay? Then store it. So you are doing the same thing here. You are doing the same thing. So we assume, log is implemented. Okay, so I'm not going to talk about log, right? Assume that this guy has a log to access this local value, log value, right? It's a little bit lengthy. So log is 0. So assume that CPU 0, already got the log variable. That means you have a permission to access this global variable. Then you can do this. You can do this operation. Okay. And after that, CPU 0 release the log, right? 1, then 0. Release the log. Then CPU 1 is getting the log to update, this sum. Okay. Then it is doing the same operation. LDR, add, then store instruction. Okay. To finally update. Okay. Then what is the problem? What is the problem with this? Why am I talking about this? Okay. So here, so LDR, then you are reading, right? So reading, sum is here. Sum is here. Then add, CPU doing addition. So initially sum is 0. Then you are adding 1. So R1 will be 1000. Then the result, partial sum should be updated to this memory location, store instruction, right? Reading from same location, reading from sum, and writing to sum, right? So you are updating this this memory location. But the problem is, we are implementing write back cache. Write back cache means what? The cache is only updated. Main memory will be updated later on. That's the write back cache, right? So why do you want to update memory later on? Because main memory is so slow. I don't want to touch main memory. That is why caches typically implement write back mechanism. Write back, that means dirty bit. Dirty bit is set to 1. Because you wrote, you updated, this cache, right? So dirty is 1. That means cache will update main memory later on, eventually. We don't know when, but cache will update, this main memory. So you see the problem, right? This main memory has still 0, right? Because you read that sum and updated only cache. Right? So we have an inconsistent state, right? Main memory has the old value, and cache has the latest new value, right? So at this point, right, CPU 1 is doing the same operation, right? LDR, reading from sum, okay, addition and store, right? So think about this. Reading from this memory location, LDR. Then what do you expect? Reading from this memory location. So you have a cache miss, right? At the beginning. So CPU number 1 is generating some transaction. Okay, I need the data, right? So then without any hardware support, cache coherent support, main memory is going to provide this, stale, old information, right? 0, not this latest information, right? Then you see the problem, right? 0, then update, 0 plus 2000, right? That is 2000, and 2000 will be updated to, this memory location only. So the problem is these two CPUs are holding same sum, but the data, it has 1000, it has 2000. So without any hardware support, you have inconsistent, incoherent state. Then what should happen? Hardware is providing a solution. So what kind of solution? Cache coherence mechanism, right? So what happens is, so second CPU is doing same operation, memory read operation, right? So generating was transaction because you missed the cache. Then that transaction is seen by CPU1. We call that snooping, right? Snooping. This CPU1 keeps monitoring this post transaction. This post keeps monitoring this post transaction. If the transaction hit the one it is caching, then we call that snoop hit. Then CPU 0 is providing this data. Not main memory is not providing this data. So 1000 is provided to CPU 1. Okay, so you have 1000 done. Now the addition, right? So 1000 plus 2000. So we have 3000, and 3000 will be updated. Then the question is, you update 3000, right? Then how about this, this data? It is still holding 1000. So before write operation, before update, store instruction is update, right? Before update, you have to invalidate. Right? So CPU is generating before update, right? Before write, before store, it is sending invalidation. Invalidation request. Okay, you have to invalidate this one. Okay. So how do you know? Because it contains each cache line contains state information, shared information, shared state. CPU is implementing this protocol message, right? Modified, exclusive, shared, invalid. We know, right? These two memory block. So these two caches are sharing the same memory block. So hardware tagging. Okay, this memory block is shared, and this memory block is shared. Right? So when you update, when you do storage, when you execute memory update instruction, cache knows because it is marked as a shared. Shared means this cache will send invalidation request to the other CPUs. The point is, for cache coherence, cache controller is providing a hardware solution. You don't have to do anything. Hardware is generating validation request. Hardware is checking the memory bus transaction. Okay. So hardware is doing everything for you. So you don't have to specially generate interprocessor interrupt for data or data coherence. But in case of TLB is not providing that kind of hardware fits, hardware solution. So you have to manage that coherence, page table entry, page table coherence by software. Again, the assumption is there are two CPUs. Two CPUs are collaborating each other. So execute one application program. That's multi-threading application. So that means same page table is shared. Not shared. Same page table is used by CPU 0 and CPU 1. And then the question is, what if one CPU is changing, updating page table? Then the other CPU does not know, right, that update. So you have to do something by software, and that is fixed by sending IPI interrupt. So let's see. Okay, so that is the application. We are talking about why do you want to use IPI? System boot up, test dispatch, and TLB shutdown. The last thing is similar to the first one. System boot up time, system shutdown time. When you shut down your computer, you have to send IPI. Okay, stop. All 8 CPUs are active, right? So that guy is sending like, okay, you have to stop. Okay, you have to stop. Stop the CPU before turning off your computer. Okay. Any question about this? Any question about IPI? Interprocessor interrupt? This one is important because every CPU not every CPU is generating IPI. Intel, okay? RISC-V, every CPU is generating IPI. Same issue. We have TLB issue and startup boot up time issue and task dispatch issue in Intel machine. RISC-V machine, computer system, IPI is used. Okay, there's one. And if you still don't know about TLB, then you please check out this lecture. TLB, then some background information. So that is from computer access class. This one. Okay. So background TLB. Then lecture 11. This one MMU in Zynq. Okay. So example of this slide is discussing examples with the Zynq device, Cortex A9. The page table. What kind of format? The page table entry format, and TLB hardware structure. So that lecture is talking about virtual memory support with a specific example, Cortex A9 example. What kind of 4K byte page, 1 megabyte page, those examples. By running that program, example program, you can get better idea, right? This one, this example program, better idea, right? Because that example is creating page table in memory. Then then demo program is doing address. Demo program is generating memory transaction. Then what? Then based on this page table information, CPU is accessing some location. For example, you are generating LDR, okay, R0, let's say 1000, memory location 1000 in X. The virtual address, you are accessing main memory with 1000 virtual address. Then page table says, okay, 1000 is mapped to probably 5000. 5000. So you need to look up this page table. And CPU is accessing page table, right? And caching the entry, and that entry says okay, 1000 is mapped to 5000. The physical address is 5000. So your program accessing 1000, but in reality you are accessing 5000 in physical memory. So that is a simple example. So in this demo. Okay. So check out this TLB lecture. Okay, so let me show you one demo. Okay, before demo, let me finish the PowerPoint, right? Sending IPI, right? Sending IPI is done by writing to this register. Right? So after generating interrupt, so what do you have to do after generating interrupt? You have to follow the standard procedure. Writing to this register, then it is generating interrupt. Then in ISR, what do you have to do? Interrupt service routine. You eventually get into this ISR. Then you want to do something, then come back to interrupted process, right? So at the beginning of ISR, you have to read what? You have to read interrupt acknowledge register. Read acknowledge register. And that register contains interrupt ID. So in this SGI case, you are supposed to use one of these 16. So that ID information is contained here, and you can check out our CPU ID. That means what? Who sent interrupt to you? So here, 10 bit. Okay, there's interrupt ID. So one of these. In the demo example, we use number 3. So writing number 3. SGI. So writing number 3 to this field. Then number 3 interrupt will be generated, and in ISR you read acknowledge register, and this then 10 bit will contain that number 3. So in ISR you know, right? Okay, number 3, ID number 3, okay. And also is 3 bit. Is 3 bit is indicating who sent that interrupt IPI to you. Because we have ACP, right? Probably number 7 sent interrupt to you. Right? Number 6 sent interrupt to you. In case of number 7, you have number 7. CPU ID. Who sent that interrupt to you? But in our system, we have only one CPU is alive, right? CPU number 0 is alive, right? So CPU 0 is sending interrupt to itself. Number 0. So number 0 we writing here, then interrupt. Sending interrupt to yourself. So number 0 will be interesting. Then at the end, so there is interrupt acknowledge register read, and at the end you have to write to EOIR, standard process, right? You have end of interrupt register. So you are writing same information, the data you read. That should be written to EOIR. Data, same information should be to EOIR. That means what? That means you are telling CPU interface, okay, I'm done processing your request. That is a standard process, right? We are playing with specific interrupt controller, right? GIC, generic interrupt controller, but other interrupt controller is working very similar way, right? Other interrupt controller has the similar register, acknowledge register, end of interrupt register. So if you understand GIC completely, the other interrupt controller, very easy to understand. Okay, there is one. Let me show you a demo. Okay. This one, SGI. So I have created this project for you. So if you scroll it down, I'm generating, look at this. Okay. Inside distributor, we have SGI register, software generate interrupt register, and I'm sending IPI with that instruction. So before writing to this register, okay, I'm creating this one. Okay, you need to do what? You need to cook up data based on that format, right? Cook up data based on that format, right? You have to specify target with green and orange, then interrupt ID. So in this example, ID is number 3. Okay, ID number 3. Okay, and then target is one 16-bit shift left, right? Why 16-bit? Because a target, right, field start from bit 16 to 8-bit, right? So I'm one shift left by 16-bit. Then you align that one to that position. So write 1. So that means what? I want to send the interrupt to myself. So here you have bit 16. Everything is 0 except the rest. So I want to write these 7 zeros and 1. Okay. to generate interrupt myself. And then this field green 00, right? Green 00. So that is SGI generation. But before that, you have to do what? You have to program, right? Distributor and CPU interface, right? Initialization, right? So what? Priority setting. Priority. So we are setting interrupt ID number 3. So what is the priority? So you have priority register, right? And you have to set up, you have to assign some value. And also threshold, right? So in private master register interface, right? You have to set up your threshold. So number 3, in other words, number 3 related register setup in distributor, right? Number 3 related register priority and also enable, interrupt enable, right? So we have global distributor enable, then this number 3 enable, then target is specified here, right? You don't have to set up target, right? And CPU interface, mask, right? And also enable, right? CPU interface is hardware enable. So the code before that is doing that setting. So let's follow this. So we have our own interrupt vector table, and this one is the one, right? 18 offset 18. How do you interrupt? Because that interrupt will be delivered through that IRQ. We have FIQ, IRQ. So interrupt is generated through IRQ, then offset 18. Okay. Will be offset 18 will be accessed. Right? We have branch ISR. Right? So that instruction will be accessed. Then first instruction, change processor state, right? Interrupt disable interrupt, right? So CPSR I bit, you want to set I bit to 1. Why? Because you don't want to take interrupt, right? CPU number 0. Okay, I don't want to take interrupt because I didn't set up the distributor and CPU interface yet. After setting up these two guys, then I will enable interrupt. Disable interrupt, then vector base location, right? So we are going to use our own vector table, right? With that code, right? Then stack setup, change processor state to IRQ mode. Then stack pointer setup, okay? Then GIC setup, right? Important thing is distributor enable, right? That hardware. The whole hardware enabled. Then priority setup. I need to touch priority number 0 register because each register is holding. It's holding what? Four priorities, right? 4 different priorities. Taking care of four interrupts. ID number 0 to ID number 3. So we are talking about ID number 3. So that is why you need to program this register, priority number 0, right? And 8, priority 8 is assigned for ID number 3. So we shift 8 to 24 bit, okay, to position that into that byte location. Then your CPU interface, right? Enable. Then threshold setup to lowest. Okay. Then interrupt generation. Then change it to interrupt enable. Then user mode. Right. Then CPU will execute this forever loop, right? Continuously. Then eventually, once you write to SGIR, right? Here. Once you write SGIR register. With that instruction, hardware is doing some operation. Think about it. Hardware is checking priority, right? Checking priority because potentially there are 1020 inputs. Right? So this priority who among these 1020 potential inputs. Right? Who has the highest priority? Hardware is doing checking that operation. Think about hardware design. If you are hardware designer of distributor, what would you do? There are 1020 priority register. You have to compare 1020 because highest interrupt should be sent to CPU. Right? So distributor is doing some operation, hardware operation, and send that into CPU interface. And the CPU interface hardware is doing some operation, some comparison. Because threshold, right? The priority should be compared against the threshold, right? And check out this enable is done, right? Some hardware operation. So that will take some time. This hardware operation, then finally forwarded to CPU. So after writing to this register, okay, CPU is doing this operation. The hardware is preparing it and send it to the CPU. So let me execute that code. SGI. Okay. Okay, so here F5, right? So vector base setup, then stack setup, and distributor enable priority setup for ID number 3. For ID number 3. Right? So you can check out this MP core. You can see a bunch of registers in this GUI. What do you have priority register? Can you see priority register? CPU interface, CC, right? And D, distributor. This is, I don't know. Can check this out. Then CPU interface, enable, then threshold setup. Okay, so now, right? Do we have SGI here? Okay, here we have SGI. Right? Software generated interrupt register. Software SGI. 5. Here, writing. Okay, writing. Then forever loop. Okay. So let me. Did I set a breakpoint here? Okay, I set a breakpoint. Let me press F8. Then eventually it will stop there. Okay. Vector offset 1.8. Right. Then F5. Then acknowledge rate. It's cute. Something is cute. Okay, let me do it again. I don't know. Let me compile it again. I think I typed something. me just press F8. Right? Then we'll stop here. Then F5. Okay. Then acknowledge register read. Right. So if I press F5, then R3 register contain. R3 register will contain ID, right? 3. Right? So R3 register. So by looking at this, right? So we know, right, interrupt ID and who generated interrupt, right? CPU number 0 generated interrupt with ID number 3. So now, toggle LED. Okay. Toggle LED, then end of interrupt update, right? Then, okay, you need to come back. You need to go back to interrupted place by executing this instruction, right? You need to do a -4, right? So forever loop. Okay, any question about this demo? An IPI? 지성, question? Okay, Guyun, what do you think? We can finish a little early. That is everything I have. If you don't have any question, we can finish a little early today. Question? Yeah, ask any question. Yes. Second task. Okay. Okay. 안 들려. DC motor. Servo motor. Yes, servo motor. That is servo motor. Yes. Servo motor. Yes. That toy motor, right? Toy, small motor. So this one is like, self-driving car, right? So that is the one, right? Car, while, while driving, while, self-driving, motion sensor is detecting, I don't know, motion sensor is detecting what? Speed and direction and trying to control, servo motor, right? I don't know. The scenario, okay, you can imagine. Okay. So ultrasonic sensor can measure the distance between car and wall. Some virtual self-driving car environment, right? So about this, right? Sensor. So inside a car, right? So you want to read a book, I don't know. You can think about this, virtual self-driving car environment. So if you are late, again, we have only 2 lectures left, okay, 25th and 30th, right? And the 1st of June, election day, 6th of June, Memorial Day, holidays. So we have, then the class projects due on 7th of June. Then your presentation, right? We are going to spend we are going to use 3 classes, 8th, 13th, 15th, for your presentation. Okay. 6, 10, 14. I think 14, right? So that means 5 of you disappeared, and that means gave up, right? So we have only 15. So 5 students can present in one day. So you can use 15 minutes, I think, in each class. And we are, yes. So what I asked is what? So you probably prepare this video clip. Okay, video clip. Then here you can play that video clip. Okay. Then I'm going to ask some questions from time to time. Right? Interrupt you, then ask some questions. And PowerPoint, right, should be prepared. PowerPoint. Okay. Any other questions? Okay, that's it. That's it for today.